Okay, good morning, everyone, and welcome to the fourth lecture of Mime 3380. The last example we covered was this system. It could represent a corner of this um, system shown in the figure, which essentially shows how the suspension in that corner of the car behaves. The goal is to know how much of the motion coming from the road, which we show with variable u, will end up to be transferred to the passengers. The goal, of course, is to minimize that motion. So we don't want to feel a bump when we travel on a road. Um, but before doing anything about it, you need to understand how this system behaves. So you need to know the math behind the system. You need to know the model of the system before doing anything either to the parameters of the system, like changing the stiffness, changing the damping ratio. Now, changing the stiffness could mean changing your tires. Essentially, changing a tire is equivalent to changing of stiffness. Or at the time that you're making this car, you can decide to strengthen the chassis, to give the chassis more stiffness or less stiffness, get a higher capacity damper, for example. These are the things that you can do at the design level. But before doing anything to the design, you need to know the basic behavior. You need to know the model for this system. So if you recall, we started by, of course, the physical system as is shown here. There are two inertial elements. For each inertial element, we drew a free body diagram. So mass 1 is the left one, mass 2 is the right one. We show the motion of the first mass with variable q1, the motion of the second mass with variable q2, and we made an assumption. Now, this assumption is neither right or wrong, it's just an assumption. But as soon as you make that assumption, you can't flip that assumption throughout the solution of the problem. So as soon as you decided or assumed that Q2 is larger than Q1, it stays like that for the entire solution of the problem. But that doesn't limit the validity of the model. So if Q1 at some point, as these two masses move, becomes larger than Q2, this will be taken care of by change of sign. How? I can show you here, for example. When we start writing Newton's second law for the first mass, we have m1 q1 double dot. That's m times acceleration. When you add all these forces, there is k1 q1, which has a negative sign because it's in the opposite direction that we call positive. And we have k2 times q2 minus k1. So we make that based on the assumption that we made that q2 was larger than q1. That means this second spring will be stretched. Now, stretching that spring means the force that the spring applies to mass 1 would be in what direction? The force that the second spring applies to mass 1, if it is stretched, would be in what direction? It would be, use the direction of positive Q1 to tell me. Is it in the same direction as Q1 positive? It is. And that is why it appears with a positive sign. It appears with a positive sign when we add all the forces. Now, when you go to the second mass, the same force is now the force that is applied to mass 2, that is, it is now in the negative direction of Q2. That is why the exact same force appears on the right side of Newton's second law written for the second mass with a negative sign. Now, what if Q2 at some point becomes smaller than Q1? That means now the spring is compressed. If Q2 is smaller than Q1, it means the spring is compressed, which means the direction of forces would switch on both of these masses. So if that happens, this becomes negative. Inside the parentheses, you would have negative, so that takes care of change of sign and change of direction. So this lengthy conversation was to tell you that making the assumption that Q2 is larger than Q1 will not limit the validity of your model, will not make this model's validity limited to only cases where Q2 is actually larger than Q1. It's just an assumption for writing the equation. Any questions on what we did? Are you comfortable with these two equations? The two second-order differential equations. So what I said was we have as the model for this entire system. Now, we mentioned the purpose of the modeling, but let me repeat it. The purpose of this modeling is to know how much of the motion, the roughness of the road, will be transferred to each of these two masses. Now, we may not care as much about mass 1. This is the sprung mass. This is the suspension mass that moves up and down. But we probably do care about mass. I said we don't care as much about mass 2 because that's the sprung mass. That's not in direct contact with the passengers. But we probably do care about mass 1. That represents the unsprung mass. So maybe one of the goals after the modeling is done, and if we want to optimize that design, one of the goals would be to minimize how much of the motion that gets transferred from U side to Q1 side. So that would be the purpose of modeling, which then tells you that the input to this system is what? What is the input to this system? The way to answer that question is what causes any change or any motion in the system? So the input to the system is the road surface roughness. So input to the system is U. So input is U. Now output. How about output? Let's go back to the system. What could be the output? Let's start there. We mentioned that a couple of times, but it's worth repeating again. Output could be one variable, could be two variables, could be as many as the number of state variables. Okay? Maybe we have to settle that question first. What are the state variable or state variables for this system? Yes?
Mass 1 and mass 2.
Mass 1 and mass 2 are important for us, but what property of them is important to us? The value of mass, or what you wanted to say, motion of them?
Yes.
Okay, motion of mass 1 and 2 is of importance to us. Okay, so that is defined by what variables? Q1 and Q2. Okay, so let's go and talk about state variables. And we said every time we have more than one state variable, we are going to use the vector notation. So Q1 and Q2 are definitely the two variables of interest to us. So these, if we know how much each of these two masses have moved, then we know a lot about the system. But that's not all. We said the number of state variables is equal to the order of the model. Do you remember that? So a first order system had one state variable. A second order system had two state variables. So what do we have as the model of the system? We have one second order differential equation and then another second order differential equation. And we need both of them in order to predict the motion of these systems. How do you know that you need both of them? Why is not sufficient? One of them sufficient? Equation 1 or 2. So if you call this equation 1 and call this equation 2, my question to you is why equation 1 by itself is not sufficient to give me the motion of this system? In other words, to give me Q1 and Q2. So it describes how Q1 double dot is a function of the rest. So in other words, it tells you how Q1 changes with time. So if you solve that differential equation, you essentially get an equation on how Q1 changes with time. But you're absolutely correct that it has Q2 in it. It has Q2 in it, but it doesn't tell you how Q2 changes with time. So you need the second equation, second differential equation to get that information. Now, we have two second order differential equations, which for each we have two state variables. So let's focus on equation 1. What are the two state variables associated with equation 1? Do you remember the key that I gave you on how to find state variables? It was last time. I said in order to find the state variables, you need to look at the differential equation and figure what variables are being differentiated. Those are the state variables. So if you look at the first one, Q1 is being differentiated. Q1 dot is there because in order for you to arrive at Q1 double dot, you need to have Q1 dot. Let me repeat. So what you see is Q1 dot is being differentiated. Can you see that? In order to have Q1 double dot, you need Q1 dot. So that equation 1 gives you two state variables, and one of the state variables obviously is Q1, but the second one is, I'm going to write it as the third state variable here. The second one is Q1 dot. So let me show you the first equation again. The fact that we have Q1 double dot immediately tells you that Q1 dot is one of the state variables, and we already established that Q1 was also important because we needed to know the motion of that mass. So in other words, position and velocity of mass 1 are the two state variables coming from the first equation. How about the second equation? What two state variables would come from the second equation? Position and velocity of the second mass. So we already included position of the second mass. I'm going to now include the velocity of the second mass. And these four together form a column vector. To identify that it's a column vector, I'm going to put a little t next to the bracket to say that in reality what I mean is this. I mean this is this kind of vector. So it's Q1, Q2, Q1 dot, and Q2 dot. That's the meaning of that little t. That's the transpose of the row vector, which gives you a column vector. So we have four state variables. Now we need to talk about the output. Which one or ones of these state variables could be our output? As soon as you say output, essentially you're saying, what do I care about? Do I care about Q1, Q1 dot, Q2, or Q2 dot? I want to relate you, the input of the system, to which one of these four variables? And what is your guess or answer? Do you want to see the system one more time? So Q1 could be your interest, but Q1 double dot is not one of the state variables. Q1 double dot is a function of the other state variables. So if you want to know Q1 dot, if you know Q1 and Q2, you have Q1 double dot. See that according to equation 1, Q1 double dot is a function of Q1 and Q2. So if you have both of them, you're all set. You have Q1 double dot. So it's not in other words, it's not an independent variable. It's a function of the other two. So again, I should say that there is no right or wrong answer here. It's the purpose of modeling. What is it that you care about defines the output of the system. So there are a number of possibilities here. So possibility number 1 is you can say, I want the output to distinguish these possibilities from each other. I'm going to number them. Not that they need to be numbered. So Y1, for example, could be Q1. You can simply say the purpose of modeling is to relate input U, the road roughness, is to how much mass 1 moves. You can say, I don't really care about Q1, but I really want to know how much mass 2 moves. Then your output would be Q2. You can say, I care about two variables, and those two variables are Q1 and Q1 dot. I need to know the position and velocity of mass 1. So that's another choice for output. You can say, I really want to know what the second mass position and velocity are going to be. That's really my interest in modeling. Do you see how various choices will give you various outputs? Or you can say, I am really, I forgot to name these sequentially. Sorry about that. So this therefore would be y3. This is going to be y4. So this is y3. This is y4. And you could also say, I really need to know all of these. In order for my design to work or for my optimization to work, for whatever reason you have to model the system, you need to know all of them. In that case, you're saying my y is essentially equal to x. So y is going to be a vector, 4-dimensional, and it's going to be equal to x. Okay, any questions on what we did? So if you want to quickly review what we did, whenever we have a mechanical system, the very first step that you have to establish is the free body diagram or free body diagrams. If you have more than one inertia element, then you decide on the positive direction of motion variable. There are two motion variables here, Q1 and Q2. They define how much each of these two masses move. Then you go to the law of physics that apply here. Like any other modeling practice, you write Newton's second law for each of these two inertia elements, and then you can rearrange it to look like the forms that we are more familiar with. So one variable and its derivatives stay on one side, and the rest of things go to the other side. So if you look at equation 1, what I did to rearrange it is I kept Q1 double dot and Q1 terms on one side and pushed everything on the other side. And if you look at equation 2, I kept Q2 double dot, Q2 dot, and Q2 on one side and pushed everything to the other side. And there is a reason for that. The reason is, if you look at the standard second order differential equation, what do we call a standard second order differential equation? So standard So the standard second order equation, whenever we talk about it, we mean this. If you talk about a mass damper spring system, it has a differential equation that looks like this. Because of that, whenever we have a second order differential equation, we try to push all these variables with similar names into one side. So x double dot, x dot, and x, it's similar to having q2 double dot, q2 dot, and q2. Now, what is the benefit of that? The benefit of that is whatever we know about the behavior of that mass damper spring is going to be applicable to other problems. It's going to be applicable to other problems. It may not be a bad time to review what we know about this mass spring damper problem. You remember that we did develop this differential equation, don't you? When was it? It was on this slide. Do you remember that? So we arrived at, back on this slide, we called the motion variable y, but it doesn't have to be y. You can call that x. If that happens, then you're different, and we call the force coming into the system r of t, but you don't have to call it r of t. You can call it F. So if that is what you do, in other words, if you have a system that looks like this, so if you have a mass here attached to a spring and attached to a damper, and its motion is defined with variable x of t, and there is an external force F of t applied, and the stiffness is K, the damping coefficient is B, your differential equation essentially looks like mx double dot plus bx dot plus kx. Where do we get that? How do we arrive at this differential equation? So you start with, what is the very first step? It starts with F. Free body diagram. So the very first step, please never forget that. Even if you know the answer, please always start with free body diagram. So the first step is free body diagram. Once you establish that, you see there are three forces applied on this system. What are the three forces? One of them is the external force F of t. The other two are from the spring and from the damper. If you write the equation for all three of them and put it into Newton's second law, that's the equation you get. Mx double dot plus bx dot plus k. Why this is of importance? Because you took an entire course on the behavior of this system. So you know a lot about the behavior of this system. So whenever you have other systems that don't necessarily look like this, you try to rearrange the equation to look like this so you can take advantage of what you know. Is that clear? So again, I told you all about that to tell you why I started from the equations I have in the middle of a slide and rearrange them to look like equation 1 and 2. Can you now see that? Now in equation 1, I don't have the first derivative. So I will not create one for the system to look like, but still I can take advantage of the comparison between equation 1 and the standard second order equation. If you compare equation 1 to this last equation that I have, let's call it equation 3. If you compare equation 1 to equation 3, what is your immediate conclusion? You have the equation 1, so I'm not going to switch back to this slide. So if you compare equation 1 to equation 3, what are some of the lessons you can draw immediately? Absolutely. So there is nothing that damps the motion of the first mass. So theoretically, as soon as you get that mass moving, there is nothing to dissipate energy. So that's one. Now the other thing is what? The other lesson that you can draw by comparing equation 1 of the previous slide and equation 3. Look at the right-hand side of both equations. Comparing right-hand side of equation 1 to right-hand side of equation 3, what is your observation? What?
K2, Q2 are the force.
So K2, Q2 is what causes mass 1 to change, which is the same way as F causes the motion in the third equation. Can you see that? So if Q2, in other words, is 0, mass 2 doesn't move, the immediate conclusion is so if F of t is 0 here, what will happen to mass? The mass here. It won't move unless there are some initial conditions. Unless you have already pulled the mass away. Of course, there is no force applied to it. But if you pull the mass away from its equilibrium, it will move until it reaches back to the equilibrium. But if it is at equilibrium, which means zero motion, zero displacement, and zero velocity, and zero acceleration, if there is no force, it will stay where it is. And that is exactly what will happen to, according to equation 1, that is exactly what will happen to mass 1. If there is no motion in the second mass, if second mass is motionless, Mass 1 will not move unless there is some initial energy into the system, initial condition into this. So what I'm getting at is by taking new differential equations and rearranging the terms, you can learn a lot simply by comparing to the systems that you have worked with previously. And that's exactly the same approach we took with the first order differential equations. Didn't we do that? We said if you have the first order differential equation and you bring all the variables with x and x dot to one side, and you make the coefficient of x go to 1, the coefficient of x dot is going to be your time constant. As soon as you have the differential equation, you have some information about the speed of the system. So that's the approach we are trying to take here as well. Okay, so this is your first challenge question for the day. So I want you to derive a set of differential equations for the system. Which one do you want to do? The first one, second one. We'll solve one of them, and I'll leave the others for you as practice problems. So which one would you like to work on in class? Are they equally unappetizing at this hour of class? So let's just go with maybe A, the first one, because it's on the top. So I'll give you a couple of minutes. Try to set this problem up, please. Let me know if you have any questions, and I'll walk to your desk and I can explain or we can discuss if you have any questions. Okay, so we have mass 1 and mass 2. For each of them, we'll draw a free body diagram. So I have started the free body diagram at the top of the slide. This time, for a change, let's assume that x1 is going to be larger than x2. For the previous problem, we assumed q2 was larger than q1. So for this one, let's assume that x1 is larger than x2 at this instant. Okay, so to mass 1, we have the spring attached. So if mass moves to the right, spring force would be opposing the motion. So we have one force for the spring, another one for the damper. Now let's look at the system one more time. So we have the force of spring. What would be the force of the first spring? How much force would spring with stiffness K1 apply to mass 1? It would be what? It would be K1 x1, so K1 x1. And the damper would be B1 times x1 dot or x1 dot. So two of the forces, let's look again. There is this middle spring, and we assume that x1 is going to be larger than x2, which means what? What would be the status of a spring if x1 is larger than x2? And the direction of the force would be on mass 1. What would be the direction of the force if x1 is larger than x2? It would be opposing x1 or in the same direction as x1? It would be opposing. So if x1 moves more than x2, the spring would like to apply a force opposing. So the force would be a K2 so K2 times x1 minus x2. Any other force applied to the first mass? How about gravity? So anywhere on Earth you have gravity, but should we include gravity? If not, why? What's your answer?
Well, we should include it because in this case we have to take into account friction.
You're saying we should or should not?
We should.
We should, and the reason is because there is friction.
Yes.
In here, you're saying in the second mass. So for mass 1, you're saying it's well lubricated, so there is no friction.
Yes.
Okay, so it should be included or not included for mass 1?
For mass 1, no. For mass 2, yes.
But for both masses, we do have the effect of weight. You're saying the distinguishing factor is friction, and we know for Coulomb type friction, so if we assume that type of friction exists, weight would play a role because that defines the amount of friction. But let's just put friction aside because we just settled the question of friction. As a force, should we include it or should we not include it, and why? Why is that? So the correct answer is the weight is there, but we are not looking at the y direction motion. If we were to write Newton's second law in the y direction, W would show up. But here, it doesn't because we are limiting the motion, or our interest, in other words, is in the horizontal motion, and W is not in that direction, or doesn't have a component in that direction. That's why. If we were on an incline, W will show up in this equation. If we are on an incline, W would show up in the equation of motion here. Okay. So we're done with the forces applied on the first mass. Let's move on to the forces applied to the second mass. So if x1 is more than x2, the force applied to the second mass would be in the same direction as x2. We have a third spring. Let me show you the picture one more time. We have a third spring with stiffness of K3, and its end is being stretched or compressed by variable y. It's another motion. It's another displacement. Now we need again, to make an assumption. Is x2 larger than 1 at this instant, at this time, or y is larger than x2? Either of the two assumptions is going to be correct. There is no wrong or wrong assumption. You just need to make an assumption. So if you make an assumption that x2, for example, is less than y. So if x2 is less than y, the direction of the force of a spring with stiffness of K3 would be in what direction? In the same direction of x2 or opposing x2? If y is more than x2. Let me show you the picture. If y is more than x2, what is the direction of the force? The same direction as x2. It's going to pull x2. So this is going to be K3y minus x2. Okay, what other force? Let's look at the picture one more time. We also have what other force on mass 2? Friction. And our interest in this course is to use a specific model of friction which is known as viscous friction. And that basically says the amount of friction is proportional to speed of motion. The faster you move, the more friction force it would apply. And this friction, the coefficient B2, essentially implies that. So we know the level of the force is going to be B2 times what variable? What is the speed of mass 2? X2 dot. So it would be Bx2 dot. What would be the direction? The same direction as x2 or opposing x2? It would be opposing x2. So I'm going to use this and write B2 x2 dot. Okay, let's review. Did we include all the forces applied on this system? Anything missing? So we included B1 from the left, K1, K2, K3, and the friction applied on the second mass. So we have everything. What is the next step? Write the equation, which means writing Newton's second law. So M1 x1 double dot is going to be equal to, okay, help me, K1 x1, positive or negative? Why? Because its direction is in opposite direction to x1. So it's minus K1 x1. How about V1 x1 dot, positive or negative? V1 x1 dot, positive or negative? Negative, because in the same direction. How about K2 x1 minus x2, positive or negative? So again, the direction is in the opposite direction of x1, so negative. All three forces in negative direction. That's based on the assumption we made for the second one. So let's move to the second mass. M2 x2 double dot is going to be equal to, so let's start with K2. Positive or negative? K2 times x1 minus x2. Positive or negative? It's in the positive direction of x2, therefore positive. Let's move to K3 y minus x2. Positive or negative? Positive. Okay. Any other force? Which is minus B2 x2 dot. Anything else? Okay, now I want you to practice in rearranging the equation. You remember the discussion we had about the rearranging the equation? So go ahead and rearrange these two equations. So if this is equation 1 and equation 2, let's rearrange them. So did I do this correctly? Please compare your rearranged equation 1 to my rearranged equation 1 and also for equation 2, and let me know if I missed anything or there's a sign mistake. Is it okay? So we rearranged both equations. Okay, so let's now discuss about input, output, and state variables. So what is the input to the system? What causes the motion to happen? Apart, of course, from initial conditions. Let's just set that aside. What variable or variables cause motion in this system? Y. Let's look at the picture. So Y, which is motion applied to the end of the third spring, that is what causes, that's what comes from outside the system. So Y is our input. So input even though most of the time we reserve variable y for output, just so happened that our input this time is called y. So state variables, what are they? What are the state variables? I'm going to rely completely on you guys now. Okay. So x1, x2. How many should we have? 4. Okay. So we have so far 2. We need 2 more. x1 dot and x2 dot. Very good. Thank you. Output. Unlike input and state variables, output is not a set answer. It could be any combination of state variables, depending on what you want from this system. What is the purpose of modeling? So I'm not going to repeat it, but any of these state variables or any combination of state variables could be your output, depending on what really interests you in this system. Okay, so please use these two as practice problems. I believe those are part of homework, assigned homework, so you do have access to final solution. Of course, the steps are not there, so you need to solve it and then check your final answer. And this is an interesting problem. The concept of active suspension has been fascinating us for probably as long as we had any suspension in cars. So the question is, can we really counter any motion that comes from the road or any reaction that is caused by maneuvers of the car? So as the car cornered, typically the inner side would tip in and the outer side would, as you can see in this car. So this car is going through some cornering, and so you have basically tilted the car. Can we keep the car horizontal? And the reason it's tilted is because of the acceleration applied on the car as it goes through a curve. So can we keep the car calm, horizontal, essentially motionless all the time? And we know we can play with the stiffness of the spring and with the damper, but at the end of the day, we can minimize the motion, but we can't get rid of it completely. Now, the solution is if you have an actuator, something that causes motion within your suspension system, and that's why it's called an active suspension. So if you look closely at this suspension here, these blue objects are not dampers, are not springs. They're actually motors, linear motors pushing against the wheel between the wheel and chassis. So if the wheel is coming up to push the chassis up, this basically linear motor would push it down. It will counter it. If on the other side, the wheel is going down, you have a pothole, and the chassis will follow, it will basically pushes the chassis away to keep it horizontal. So that's the simple way of describing. Of course, it happens very quickly. You need to rely on sensors, on computation. This is a control problem, essentially. But what interests us on the modeling side is how to write this a mathematical equation for an active suspension. You can basically simplify that like a regular suspension, and the effect of that linear motor is captured with an additional force, which varies all the time, like any other variables in the system. So if you look closely, we have, again, the stiffness of the tire, the stiffness of the spring for the suspension, and partly the chassis. We have the damping causes from the tire itself and the the damper that we actually have in the suspension. But in parallel to these two forces, we have this force U, which comes from that actuator. Do you see that? The force in the middle. So, would you like to give this a try? To write the equation of motion for the system? Yeah, yeah. So take 30 minutes, not minutes, seconds, and write this. So we have x1, motion of the body mass, x2, motion of the suspension mass, m2, and then w, the road roughness. So go ahead and write the equation. And you can make the assumption that the motions are measured from equilibrium, static equilibrium. So the effective weight is captured by initial compression of the two springs. So you don't have to really include weight in your equations because of that cancellation. Okay, so these are the two free body diagrams with the two assumptions that I made. X1 was going to be larger than X2 at this instant of time, and X2 larger than W, again, at that instant of time. Based on that, I wrote these expressions for the forces. Let me know if you found something different, and I'll correct. So U is applied upward on the first mass and downward on the second mass. That is the force coming from the actuator, the linear motor. Everything else is the force of the two springs and the force of two dampers based on the assumptions that we made. Okay, I'll let you finish the rest to write the equations, to rearrange the equations. Please complete that. Um, so what I'm asking to you to do next is write the two equations of motion and then rearrange them to look like more of a standard form. This is another interesting example. I'm sure you've come across equation for pendulum. It's a typical vibration problem or vibratory system. If you deviate mass from its equilibrium at the bottom, it will just go through a sinusoidal type motion. So it is important because this is a nonlinear system. And I want you to see that. I want you to see that this is a nonlinear system. So why don't you go ahead and give this a try and try to come up with the differential equation for this system. Again, you need to start from a free body diagram. The assumptions are that the link of length L doesn't have a mass, so its mass compared to the mass of the tip is negligible. So we assume that there's only one mass at a distance L from that hinge. So at the hinge, we have two reaction forces applied to this link. I've called them OX. So the force applied in the X direction at point O and OY. These are the two forces. And then we have mg as the weight applied because of mass. And that's where vertical. It's going to be in negative y direction. Of course, we can also include friction of the joint, but for now, let's not include it. Um, But we can make the exact same assumption as we did for linear motion and assume that at the hinge we have a viscous type friction. Or let's include it so it would be a more general solution. So having a viscous type friction means that we are going to have as this link moves in counterclockwise direction, the friction would apply a moment at point O that would oppose this motion. So we can show the effect of friction with a moment that is going to be clockwise. And this is going to be B times theta dot. That's the meaning of this being a friction, a viscous type friction. So it's proportional to how fast this link rotates. So it's if it is stationary, there is no friction. The faster it moves, the more opposing moment is applied to slow it down. So this is the free body diagram. Do we need to include anything else? Seems like we have captured what we assumed to be there. So we didn't consider, for example, the elasticity of the link. So we are assuming the link is rigid. So one variable theta describes the motion. And we further, so it's a very stiff link, so it doesn't deflect as the mass m moves. And we further assume that the link has no mass. Otherwise, we should have included the weight of the link in its middle somewhere. So we have simplified. We have made assumptions to simplify this problem. Okay, what is the next step? Now that we have the free body diagram? The equations. What is the equation that we write? For linear systems, we wrote what? Mx double dot is equal to sum of all the forces. What do we write here? In rotary systems, instead of m, we write moment of inertia. So it's not the mass only, but how far it is from the pivot point. How far it is from the pivot point. So it would become I about point O theta double dot is equal to sum of the moments also about point O. So that point becomes important, point about which we are writing the equation. Now for a point mass, do you guys remember what I about point of mass m is going to be? Did you say 1/2 ml squared? So it's 1/2 ml squared. That's moment of inertia of mass m about point O. Essentially, that captures. Now, inertia is basically tells you how difficult it is to move the mass. The more mass you have, the more force you need to create acceleration. The same information is here. It basically tells you how difficult it is to rotate this mass about point O. So it makes sense that the value of mass is involved, but its distance is even more important. That's why the distance appears with power 2. So the distance is even more important in how difficult it is to rotate the mass about point O. That's basically the essentially the information that is captured in moment of inertia. Okay, so we know what I is. Theta double dot is the angular acceleration. So theta double dot is angular acceleration. And now we need to look at the right side of the equation. What are the moments involved? So let's write them down. So where should we start? The first moment is caused by, So moment is force and the moment arm. So the moments of OX and OY, what are those? 0 because? And because there is no moment arm. So they're at no distance from the point of interest. Therefore, no moment for them. How about mg? Does that create a moment? Okay. And that moment is equal to what? It's mg times what? Times the moment arm. And what is the moment arm? The moment arm is this distance. Can you see that? Why that distance and not the vertical distance? So in other words, why not this distance? Or not? Why not this distance, the distance L? What is your answer? So what we care about is the distance perpendicular to the force to the point of interest, the point of rotation. So that's the perpendicular distance. But what is this distance? Of course, it changes as the mass moves. So if we are at the very bottom, when theta is equal to 0, that distance is also 0. When theta is equal to 90 degrees, pi over 2, that distance is equal to L. In between, the distance changes. So what is that distance? It is L sine theta, exactly. So it's L times sine of theta. So what is the moment then? The distance is L sine theta, and the force is mg. So that's the first moment. mg L sine theta or L sine theta mg. Now what is the sign of this moment? Of course, we have two choices, positive or negative, but we need a reason. Okay, why do we call it positive? So that's one option. B theta dot going in what direction? So the way to distinguish is clockwise or counterclockwise. So B theta dot is creating a clockwise moment. How about mgl sine theta? Okay, so then positive or negative? So the way to tell is based on what you call positive theta direction. So what is positive theta direction? Clockwise or counterclockwise? So positive theta is counterclockwise. Therefore, any moment that is clockwise is going to be negative. So this needs minus. And immediately, you can see that B theta dot is also negative. Okay, the next step is to rearrange. So it's going to be 1/2 m L squared theta double dot plus B theta dot plus m g L sine theta is for now equal to 0. But if we had an external moment applied, if we had an external moment applied about point O, that would end up being here. Should we? Let's not include it. Let's just put 0. So there's no external moment applied. The only moments are caused by motion of the mass. Okay, now compare this to m x double dot plus b x dot plus k x equals 0. Similarities start with inertia. Linear inertia is mass. Angular inertia is 1/2 ml squared. So it has to do also with the distance, and the distance even is more important than the mass. It's power 2. Damping, we assumed similar type of damping or friction, B x dot, B theta dot, similarity. Now when it comes to the portion of the system that stores energy and releases energy, in the linear system we have the spring, something that deflects and stores energy and gives it back. So potential energy stored gives back as kinetic. So what has that function for our rotary system? What stores energy and releases energy? It's the mass itself. As you move the mass from that bottom equilibrium, as theta becomes non-zero, you start storing potential energy in the mass itself. You start storing energy similar as if you had a spring in the linear system. So that's the effect of it. So that's the similarity. So now K is the stiffness of the spring. What is equivalent here is the mass, the gravity, as well as the length. You can see that. You can see mass, G times L collectively plays the role of K. So if you have more mass, more gravity, or farther away from the pivot, it is equivalent to having a more stiff system. So more energy per unit displacement is stored in your system. Can you see that? Okay, so these are similarities. What is the fundamental difference between these two equations? The second equation is what we call a time-invariant linear differential equation. What we have at the top is still time-invariant, which means the parameters of the system, such as M, L, G, are not time-dependent. They're all constant. But what makes it nonlinear is the fact that we have, what makes it nonlinear? Sine of theta. Sine of theta. If that was theta, even though it's rotation, it's still a linear differential equation. But sine of theta, what makes it a nonlinear differential equation. So this is a time invariant non-linear differential equation. Because of sine theta. So that's the reason. Not because of theta, because of sine theta. Okay. Here's your challenge. Find the equilibrium or equilibriums or equilibria, I should say, of this system. Other name? You're more familiar with the steady state position. So what is the steady state position for theta? Where would theta settle? At what position would it settle? And you need to find it. Of course, you know the answer. You don't need to do any calculation, but I need to find it from the differential equation. So go ahead and use the differential equation and find the steady state response, also known as equilibrium positions. So what is the approach? What do you need to do to find equilibrium position? Or steady state? Yes, so that's the definition. So when you are at equilibrium or steady state, things don't move anymore. So you don't have any more motion, which means theta dot is equal to zero. No velocity. Velocity or change in theta is zero. Theta is stationary. And it has to be also that theta double dot is zero to keep it stationary. So if you set theta dot equal to theta double dot equals 0, what do you get from the differential equation? What you get is mgl sine theta is 0, which means what? And this is called theta equilibrium, which tells you that theta equilibrium is what? What value of theta will make mg sine theta equal to 0? One of the possibilities is 0. Is there another possibility? Let's look at sine theta. So this is sine theta. Sine of theta at theta equals 0 is 0. But is there another angle at which theta is 0? That's pi. That's pi. So 0 as well as pi. There are two positions at which the system would be stationary. So the 0 is obvious. If you bring the pendulum to the bottom position and make it absolutely motionless and let it go, it stays there. You can imagine that. But the reverse is also true. If you bring it up exactly vertical, that's the pi position, and keep it exactly motionless and let it go, it stays there. Even only for a moment until something disturbs it. But if there is no disturbance, nothing that causes this to move, it could stay up there. So there are two equilibrium positions. One of them is called stable. The other one is called unstable. So when it's at stable, it would always if you deviate it from 0, it always wants to go back to 0. The reverse is true. If you disturb it from theta equals pi at the top position, if you just slightly disturb it, would it like to go back to pi? It would like to go back to 0. So therefore, one of them is called stable equilibrium, the other one is unstable. So let's write it. So this is stable. So when we have a nonlinear differential equation like this, we are really at a disadvantage because I can't apply what I know from a mass spring damper system to this system readily because of the existence of sine theta. Can you see that? Because sine theta is there, I don't really have a differential equation that looks like my mass damper spring system. So it would have been nice if I could arrive at an equation that is similar to the top equation but would be linear. So instead of sine theta, I would have theta in it. So from calculus, do you remember a method of linearizing? It's called what? Does Taylor series expansion ring a bell? So it's basically finding an equilibrium mathematical description that is linear. Now, if you want to look at it graphically, this is a sine wave. It's theta versus sine theta. Linearizing means if you look closely at each portion of this, you can find a line that is very close to this curve. Can't you do that? So if you're here, for example, let me give it a try here. If you're here, you can draw a line that passes through 0 and is very close to your curve. Can you see that? If you're here, on top here, your line would be like this. A horizontal line rather. If you're here close to theta equal to pi, you can draw another line. I want this to pass through pi and be really as close as possible to a line. Like that. So a line, even though what I have is not with one slope, but a line that passes through. Now you can see what we mean by linearizing. So it means that you choose your neighborhood of interest and come up with a line that represents sine in that neighborhood. with the understanding that as soon as the neighborhood changes, that line also changes. Do you know what this line is? What is the equation for this line? It's a line of slope of 1. So it's a line of a slope of 1, which means, so if this is sine theta, so if your y equation is sine theta, this y equation here, y is equal to theta. What is this equation? It's y equals 1. What is this equation? This is y equals negative theta. So it's a slope of negative 1. So y is still a function of theta, but instead of being sine of theta, it's a linear function of theta. Do you see what we are doing here? So we are choosing in a neighborhood of interest, and we're finding the line that is very close to that point. Now, the farther you travel from this point, the line becomes farther away from your sine function. So that is the essence of linearizing nonlinear differential equations. So what we could do, let me add another page. What we could do is we can, so what was our equation? Our equation was 1/2 ml squared theta double dot plus b theta dot. What was the last portion of the equation? Is it mgl sine theta? Yep. Okay, thank you. Equals 0. So what we could do is we could choose a neighborhood and then find a linear equivalent of sine, and the benefit of that is instead of having a nonlinear differential equation, I will have a linear differential equation that is valid in that neighborhood. Not everywhere else, but in that neighborhood. Let me show you. So around theta equals 0, what we know is sine theta is approximately equal to what? Sine theta is approximately equal to what? We showed it around theta equals 0, which is the origin. Sine theta is approximately equal to what? What is the linear equation? The linear equation is theta. So sine theta is approximately equal to theta. If you're close to, theta equals 0. So we can replace it with theta. Now, around theta equals pi, sine theta is approximately equal to what? Approximately is equal to what? 0. At pi. Oh. At pi. Sine theta is approximately equal to what? What is the linear equation that we found? Y is equal to negative theta. Can you see that? That's the line equation we found. So around theta equals pi, sine theta is approximately equal to negative theta. So that tells you, if you want to rewrite the differential equation, it would be 1/2 ml squared theta double dot plus b theta dot plus mgl. Instead of sine theta, what will I write? Absolutely, theta equals 0. So what is the difference? What is this equation? It's a differential equation, time invariant, but what have we lost in the process? It is no longer a nonlinear system. Now I have a linear system. So everything that I know about the mass spring damper system, I can apply here because I got rid of the sign. So if you do the same thing here, for this case, it is going to be all the same, except for the last part, it's going to be minus mgl theta equals 0. Here's the challenge question for you. We started from a nonlinear differential equation and we linearized it. In this simplification and approximation, what have we lost? What information is no longer in my differential equation that previously used to be in my differential equation? I really like this question. You can tell. My eyes light up when I ask this question. So whenever I like a question, the tendency is that it appears in an exam or a quiz, fortunately or unfortunately. So I really like this question. When you linearize a differential equation like this, what do you lose in the process? Yes, sir. Absolutely. But what information, what kind of calculation that we could do with the original differential equation is either no longer available or you get a different answer if you do that calculation? What calculation? Yes. You are definitely on the right track. So if you, now we have two differential equations. One is valid around theta equals 0. The other one is valid around theta equals pi. So if you do the calculation of finding the equilibrium position, you remember from the original equation we got two positions, right? Theta and theta equals 0 and theta equals pi. If you do the same thing with these two equations, each of them will just give you one answer. What is that one answer? If you set it equal to 0, both of them will just give you one answer, and that is theta equals to 0. So you lose the ability to calculate the second equilibrium position. So you can only calculate one of the two equilibrium positions, one of the two steady state positions. So that's what you give up. So you find an approximation, but in the process you have lost some of the information that is embedded in the original equation. Please pay attention. I just realized that because we didn't go through the entire derivation and we just did it by just looking at the picture, I made a mistake. And the mistake is the equation that approximates sine, at theta equals pi is not simply y equals minus theta. So if you plug theta equals to 0 in here, what will you get? Theta of 0 will give you y of 0. But does this line crosses theta of 0 and y of 0? It doesn't. So we need to make it, so the slope is correct. The slope is -1. But the intercept is incorrect. What should be the intercept? Where is y equal to 0 in this line? At theta equals, look at the picture. At what theta y is 0? At theta of pi. Therefore, at theta of 0, the value of the function is, with the slope of -1, the value of function is plus pi. So if you extend that line until it crosses the theta, unless it crosses the y-axis, it will cross at y equals pi. So this needs to be modified. I apologize. I did a mistake. So this should be modified as y is equal to pi minus theta. So now if you plug in theta equals to 0, y is pi. When you plug theta equals pi, y is equal to what? At theta equals pi, y is equal to 0, which means the line crosses the 0 at theta equals pi. Now, if you bring that into this equation, to the linearized equation, so again, everything else, which means the first two terms of the equation is equal to 0, the last term becomes minus mg L pi minus theta equals 0. Now, if you find the equilibrium from the first equation, you get theta equals what? So let's call this equation 1, call this equation 2. From the first equation, the equilibrium, which means you have to set theta and theta double dot equal to 0. The equilibrium would be theta equals what? Did you say 0? Yes. So equilibrium is theta equals to 0. From the second equation, if you do the same thing, set theta and theta double dot equal to 0, theta equilibrium will be equal to what? What value of theta will make it equal to 0? Will make that expression go to 0? Theta of pi. So I'll give you a minute to look over this. If I need to go back to the previous slide, let me know. Otherwise, I'll give you a minute to catch up, and then I'll review what we did on this example. Okay, so what did we do? We started from a system that had this free body diagram. So we wrote Newton's second law for this rotational system. We arrived at this equation in the middle, where we had sine of theta. We did a calculation to find the equilibrium position. Where would theta stay, or the pendulum stay, if both velocity and acceleration were equal to 0? And we found there are two positions, theta of 0 and theta of pi, which will make the sine term equal to 0. Therefore, there are two equilibrium positions. One is stable based on the experience we have with the system, and the other one is unstable. Then the question became, can we linearize this and make our lives simpler? And the answer was yes. If you look at sine theta, any region that you focus on, you can find an equivalent line. So at theta equal to 0, y equals theta is very close to sine theta. So you can approximate sine theta with theta if you're very close to theta equals 0. If you're close to theta equals pi over 2, then you can approximate sine theta with y equals 1, because that line is going to be very close, even though for a small neighborhood, but it's going to be very close to sine theta. If you switch and go to theta equals pi, then the function of pi minus theta, a line with slope of -1 and intercept of plus pi, will give you, it would be a line that is very close to sine theta. So we took that and found two linear approximations for our differential equation. One was around theta equals 0, which we used equivalent of sine as theta. The second one was around theta equals pi, which used the approximation of pi minus theta. Now, this was what we gained. We arrived at a linear differential equation which is simpler to deal with. What we lost was the entire information that was encapsulated into one equation. With each approximation, we lost one of the two equilibria. With the first approximation, we lost equilibrium at pi. With the second approximation, we lost the other equilibrium, which was equilibrium at 0. So if you find equilibrium from these two separate linearized differential equations, you just find one of the two. So that's what you give up. And that's generally the case. When you simplify, we of course give up some information, and that's for any simplification. Okay, this is a practical example of the problem we solved. So any projectile that you want to fire, at some point you have to let it go before you fire. And this is true for things we send to the space. At the very end stage, when you release the booster, you have to be able to maintain its position. And it looks like a pendulum around pi equals, theta equals pi. It's a pendulum about the unstable equilibrium. So you have to counter the motion to keep it at the vertical position. So that's what is called an inverted pendulum. And it's a very interesting control problem. Can you think of another inverted pendulum as a typical system that you may or may not have dealt with, but you've probably seen it? Have you been to a famous sightseeing location? One of the tours that you can take is on a device called a Segway. A Segway essentially is an inverted pendulum. What is the Segway is trying to do? It's trying to keep that pendulum stable around its unstable equilibrium. Can you imagine that? That is essentially what a Segway is. As soon as you turn off the motor of Segway, what will happen? It will drop. The handle will drop, and whoever is on it will drop with it. So it continuously fights gravity and disturbances to keep that equilibrium stable. Not only that, but also goes forward or backward or turn. So that's a very interesting control problem. Okay. So we are going to switch gears and revisit what you already know in the form of Laplace transforms, because that is essential for starting from a differential equation but arriving at a different model that is easier to understand. And that model, by the way, is called a transfer function. So what we are trying to do is to start from a differential equation, but arrive at something that we'll call a transfer function. And the reason is convenience. In a transfer function, it's much easier to see the relationship between input and output, but the basic idea remains the same. We start from the physical system, we apply laws of physics, we arrive at differential equations, but then we take it one step forward and write the transfer function. And the tool that we have is the Laplace transform. Now, Laplace transform is a mathematical transformation. If a function satisfies certain conditions, such as continuity, you can find its Laplace transform. Essentially, Laplace transform is like a box. You put in a function in time, and out goes another function that is now in frequency domain. It's in Laplace domain, also known as frequency domain. Now, how do you find Laplace transform? How does that box work? It is an integral transform. So you can calculate Laplace transform of any function that has Laplace transform. But in many cases, you don't have really to run that calculation. Either you have tables of functions, or you have a tool like MATLAB. Have you ever heard of MATLAB? I'm sure you all have heard. MATLAB has a built-in function. If you give it a time constant, out comes the Laplace transform. So you can find Laplace transform very easily, readily. Either you do the calculation, which is rare, but most of the time you have access to the Laplace transform. Somebody has gone through the pain of calculation and has calculated. So, for example, this table, it comes from Ogata, the same book that I talked about at the beginning of the class. So this has Laplace transform properties. So, for example, one of the properties is if you add two functions, the Laplace transform of the addition is addition of Laplace transform of each of them. The other, which is a very important property, is Laplace transform of time derivative. You know by now that we will have time derivative a lot of times. That's what defines a differential equation. So Laplace transform of the first time derivative of function f. So Laplace transform of f dot, in other words, is s times Laplace transform of f minus f at time 0. Now, what is f of s? F of s, let me write it down. F of s is Laplace transform of f of t. So if you have Laplace transform of f as the base function, you can find Laplace transform of its first time derivative. How? You simply take the Laplace transform of the base function and multiply it by power 1 of s and subtract from it the initial condition. F of 0 is initial condition. What if you have second time derivative of function f? It's very similar. You take s and take it to power 2 and multiply it by Laplace transform of the base function and subtract from it the effect of initial conditions. The good news is we are going to assume that all initial conditions are 0. Which means what? Which means you don't have to really worry about this guy or these two terms. So going from time to Laplace domain is as easy as multiplying by equivalent powers of s. What is s? S, what is the variable that replaces t? T was time. You remember that? So when you go to Laplace domain, you no longer have time involved. You have s, which is Laplace variable, which is a frequency variable. So you don't have to deal with time and its derivatives. So that's the essence of what Laplace transform is. Now, when differentiation is equivalent to multiply by s, integration is equivalent to doing what? Dividing by s. So if you want to differentiate, you multiply by s. If you want to integrate, you divide by s. So that's the essence of Laplace transformation. So these are Laplace transform of a lot of regularly encountered functions. So if a function is 1, so a constant, its Laplace transform would be 1 over s. Let's see if I can zoom in so you can see better. So on the right side, you have, on your left side, you have the time function. On your right side, you have the Laplace transform. So Laplace transform of 1, which is the second row, unit step. Laplace transform of 1 is 1 over s. The first row says Laplace transform of an impulse function. An impulse function is a function that is undefined. So it's very large, but happens over a very short period of time. Laplace transform of that function is 1. Laplace transform of a linear function, so y equals t, is 1 over s squared, and so on and so forth. So you can see a lot of Laplace transforms, all tabulated. But the most important transforms are the one that I just explained for the first time derivative and second time derivative. And this table continues. You have access to it. So at this time, we are not going to spend a lot of time on it. But what is important is, if you have a linear time invariant system, that's the requirement. It has to be linear time invariant. If you have a nonlinear differential equation, you can't create a transfer function as an equivalent model. If you have that, if you have a linear time invariant differential equation, you can create this second way of modeling called transfer function by creating a ratio. This is the ratio. It's right here. This is the ratio. And this is ratio of two variables. As the numerator, you have Laplace transform of output. As the denominator, you have Laplace transform of input. So it's output over input in a ratio. That is essentially what that model is. So all transfer function models are going to be in the form of a ratio of output over input. So that should give you a little bit of insight why we even bother to develop a transfer function, because it's very clear what output is and what input is. Unlike differential equation that you need to have some sort of insight about the system. So that's the convenience of working with a transfer function. And let me repeat that. The assumption is that all initial conditions are equal to 0. So we don't incorporate the effect of initial conditions. Now, When we had a differential equation model, it was very easy to see the order of the system. Where would you look to find the order of the system? Order of the system? It has to do with the highest time derivative that you had. So if it was double dot, that system was second order. The same information is available to you in the form of highest power of s in the denominator. So the highest power of s in the denominator will give you the order of the system. Okay? So let's look at some examples to take this into a context. So you remember this form of the differential equation for a first order system? Let's do this. Let's find the transfer function of this differential equation. So the differential equation is a x dot plus bx equals u. So what was the input? U. What is the output? What is the output? We have only one state variable, and that's x, so there is no choice. The output has to be x. So the transfer function, sometimes is shown as capital G of s, is ratio of output, which is x, in S domain. Note that I'm using capital X to distinguish the time domain from the Laplace domain. So when we go capital, we mean Laplace domain. And to make it even further clear that we are in Laplace domain, I put a pair of parentheses and S. So to show that X is a function in S domain, in Laplace domain. So output over input. What is the input? Input. So it should be u of s, again capital, as the denominator. So how will I find the transfer function? I know this is the ratio I want, but I don't know how to get to it. So I need your help. You are the only help I have, so I'm looking at you to tell me, how can I get to this ratio? I know Laplace transformation is involved. That much I know, but the rest you have to tell me. What is the only piece of information that I have from the time domain? The only piece of information that I have is right in front of your eyes, and that's the differential equation. That essentially tells me how this system behaves. Isn't that the whole idea of a differential equation? So what I'm going to do with your help is I'm going to take this equation to Laplace domain, which means I'm going to take Laplace transformation. Curly L defines Laplace transformation. So it tells you that I need to find Laplace transform of ax double dot. I need to find Laplace transform of bx. And I need to find Laplace transform of u. All of them, by the way, is in time domain. Even though I'm not putting a curly a parenthesis against next to x dot and x, they're all in time domain. They're changing in time domain. So it's fairly simple to transform a function in time that is not determined. So I don't know what u as a function of time is. I don't know what it is. It's just a function of time. So when it transforms to s, is as simple as writing it as capital U of s. That's it. Because I don't know what function it is. If I knew, I would go to the table and say, okay, u of t is a sine function, so I know what Laplace transform of sine function is. But here, I don't know. It's just a general function, so I'm going to write the equivalent Laplace transform. And so is x of t. I don't know what x of t is. I haven't solved the differential equation. So it simply becomes, by the way, because b is constant, just stays as a coefficient. So it becomes b x of s. And this becomes a Laplace transform of x dot of t. Do we know what Laplace transform of x dot is? That was one of the properties that we just reviewed. So let me bring it up again. This was the main property. We said Laplace transform of d over dt of f of t is s f of s minus initial condition. And whenever we are doing transfer function, we said initial conditions are 0. So I don't have to worry about the second term on the other side, on the right side. But what should I write according to this rule as Laplace transform of x dot of t? Laplace transform of x dot of t, a would carry, becomes, we said, time differentiation is equivalent to multiplying by s. So it would be s times x of s. That's it. So it would be a, because it's a coefficient, s times x of s is Laplace transform of x dot. So let's put everything together. So if we rewrite the equation now in Laplace domain, I'll have a s x of s plus b x of s, and note that I'm using only capital letters for taking things from time domain to Laplace domain, is equal to capital U of s. The next step is to create the ratio, the transfer function. So the transfer function, g of s, is x of s over u of s. So for that, I need to factor x of s out here. I'll get as plus b equals u of s. So what would the ratio be? It is going to be equal to 1 over as plus b. Congratulations, you have your first transfer function model. You have your very first transfer function model between input u and output x. Now in differential equation, what was the order of this system? This was what order system? It was first, and why? Why was it first order in the differential equation domain? Because of a single dot that we had. The highest time derivative was this x dot, so this was the first order. Now look at the denominator. What is the highest power of s? It's 1. So this is a first order system. Because of power 1 of s. So you ready for another practice? This time, I'm going to ask you to transform this standard form. Do you remember we had a standard form? The standard form was this. It was t. It was t x dot plus x was u over b. Do you remember that? The benefit of this standard form was that t was what? What was t? The time constant. So if the coefficient of x was 1, the t was going to be a time constant. So take 30 seconds and find the transfer function for this system, for this differential equation. So essentially, I'm asking you to find g of s, which is output x of s over u of s. So what is that? So what do you need to do? You take the differential equation into Laplace domain, which essentially means t x dot becomes ts times capital X of s. X simply becomes capital X of s. 1 over b times u of t becomes 1 over b times u of s. And if you create the ratio of x over u, you'll have 1 over b in the numerator, ts plus 1 in the denominator. Now that should give you a general rule. So whenever you have a first order transfer function, if you make the coefficient of s to power 0, which is the constant, if your constant is 1, what is sitting next to power 1 of s is the time constant. So if in a first order transfer function, so I should say in the denominator, you have in the denominator, if you have this form, in the denominator, if you have ts plus 1, so if you have ts plus 1, where plus 1 is very important, the coefficient is the time constant. So if you are given a transfer function of a first order system, you will change by multiplying and dividing both the numerator and denominator to a form that you have a constant time s plus 1. As soon as you create that, the constant that is multiplied by s would be the time constant. So plus 1 is the most important part, the same way that plus x was the most important part, the form to have in the differential equation. So you can immediately see the speed of the system by looking at the denominator of the transfer function. So the denominator of the transfer function defines the speed of the system. Okay? So I'll put a second quiz up on Blackboard and let you know. So you'll have, again, several hours to complete the second quiz. Thank you.